We're going to move on with kind of the last main section of chapter 11. I told you chapter 11 is pretty short. The last main section of chapter 11 is kind of a big one. It has to do with pendulums. Pendulums is a really applicable, okay, or a really plain topic for us to be able to see in real life. Okay, we talked a little bit at last class about where you see pendulums the most. Okay, and where would that be?
Clocks.
Yeah, in a clock. Okay. But you still see pendulums that maybe aren't labeled pendulums all the time. Anytime something swings back and forth, right, at a park, when you go to a swing, that's a pendulum, right, even if you don't think about it. But it's pendulum. Okay, so pendulum is a mass at the end of a lightweight cord. The cord does not stretch. We assume that it's a taut cord. So it's not going to stretch, and that the mass of the cord itself is negligible. So we're not talking about something that is really heavy. It's not a heavy rope that's going to affect that the swing of that pendulum. If it is a heavy rope, then that means the mass on the end of it is heavy enough that it's going to make that rope seem negligible. Okay, so we want the mass to rope or mass to cord ratio to be very heavily on the mass side. Okay, we don't want that cord to have much effect on the swing of that. Anyway, in all of our problems that we do, the cord is going to be negligible. Okay, we have a point of suspension, which is also sometimes called the fulcrum axis. Okay, fulcrum. Have you ever heard that word before? All right, hopefully. Okay, fulcrum. Most of the time in all of our problems and in our labs, we're going to try to simulate a frictionless fulcrum. Okay, why would it make a difference that that axis point is frictionless?
So you should have to worry about it.
Yeah, it should keep going. Theoretically, pendulums should, once you start, they should never stop, right? It's going to be that conservation of energy. It's going to be a harmonious, right, a simple harmonic motion that is identical and repetitive, okay? So if we have a friction-filled axis point or fulcrum, what would that do to our pendulum?
Slow it down.
It would slow it down, okay? It would throw the period of it off, which means it would slow that thing down, eventually coming to a stop. Okay, in our real life lab, that might happen, but we're going to do everything we can to keep that fulcrum as frictionless as possible. Okay, we are going to do a lab with this part of it that usually has pretty good data, but you never know. Okay. All right, a pendulum is observed to complete 23 oscillations in 58 seconds. Find the period and the frequency. This doesn't really even need a full equation. You should be able to find these and to solve for these based on just the units alone. Oscillations per second or seconds per oscillation. That's it. Okay? So I'm not giving you a full new equation to find these. You should just be able to calculate them. Okay, so if I want my units to be oscillations per second for frequency, I should take oscillations divided by seconds. Okay, that's it. Some of you will way overthink these kind of problems. Okay, and then the period of this, if I want seconds per oscillation, I would take 58 seconds divided by 23 oscillations. And I get 2.52 seconds. What's the other unit I could use for frequency? Hertz, good. I'm okay if you label it in hertz. Either way is fine. So now if we aren't given the period or the frequency, we have the ability to solve for those based on L and G. Okay, what do we think L might be symbolizing? Yeah, good. The length of the cord is L. And what would G be?
Gravity.
Gravity, right? Pendulums, are they ever horizontal?
Maybe.
Nah. If the pendulum was horizontal, what would happen to it, right? It would fall. Gravity would cause it to fall. Okay, unless the cord was not really a true cord, right, and it was holding it in place. We want a pendulum that is based on gravity. Okay. Mass on the end of the pendulum make a difference in how fast it's going to swing.
No.
No. Mass is nowhere in this equation. Does the amplitude, okay, an amplitude for a pendulum is how far you pull it up. Okay, does that matter how far? If you pull it up to 89 degrees or if you pull it 2 degrees, does it matter?
No.
Okay, there's an extreme when we get to that amplitude, and we're going to test that in the lab a little bit. If we keep our amplitude within reasonable angles, there's really no difference. I bet if we get up to 89 degrees, it would technically make a little bit of a difference. But if we keep our amplitude within a reasonable degree, there's really not much of a difference. And we'll test that in the lab to see that as well. But amplitude or mass, neither of those go into our equation. So theoretically, they don't affect the period or the frequency of that pendulum. Okay, the thing that does affect it is the length of the cord. Okay, that's the number one thing that's going to affect the period. Okay? All right, let's try one here. Okay, do we need to cut that length of the cord in half for any reason? No, we're not talking about a radius. Okay, sometimes you guys do crazy things that I don't know where it comes from, so I'm just telling you right now, don't cut it in half. Okay? You guys will do lots of things that I never said in class, so I'm just going to tell you again, you don't need to cut it in half. Okay? All right, so we're going to find frequency, which means we'll use the equation 1 over 2 pi square root of G over L.
So like the mass is not
Mm-hmm. You don't have to use negative 9.8. Don't have to use negative 9.8. We can't take the square root of a negative anyway. No mass. Right, we talked about that. Mass and amplitude don't have an effect on the pendulum.
You know, you wrote mass at the point where I was like, where do we put this?
Just because I put it up there doesn't mean you have to use it. What do we have for our frequency here?
0.42.
0.42, and our units for frequency?
Hertz.
Hertz.
Galen Hertz.
Okay, 0.42 hertz. What if I wanted to find the period now? What could I do?
1 over that.
Yeah. If you want to find the period, listen. If you want to find the period, you don't have to plug it back into the equation that looks kind of like that. We can just say 1 over 0.42, and we should get 2.37 seconds. Okay, so 2.37 seconds means it would go here, then back to the starting point in 2.37 seconds. Okay, over, back to where it started. 2.37 seconds. Okay? Question there? Okay.
Is this what we're doing today?
This is the big section. We have one little section at the end we're going to do.
Hey, there's no. What? When's the next basketball game? Final Four basketball? Oh, I was like, Saturday. It's the national championship. Yep.
Okay, algebraically here you have to be a little bit more careful. You need to divide by 2 pi. Okay, which means divide by 2, divide by pi, or parentheses 2 pi. And then we square both sides. And then we multiply by 9.8.
I did 9.8 instead of 0.98. Oh.
Agreed? Okay. All right. So this is a little tiny section here at the end of chapter 11 I want to cover a little bit because it's pretty applicable. Okay? And it talks about energy transported by waves. Okay? And the definition of intensity is essentially power of the wave divided by the area that it's going to cover. Okay? And we're going to look at sound intensity really only. Okay? And so the definition of intensity or the equation for intensity is power over area. Okay? And I'm going to give you kind of a simplified equation that goes with that. That will be the one that we would use in our problem. Okay. Let's see. Okay, do we see where these units are coming from? Energy is joules, area is meters squared, and time is seconds. Okay, so power is joules per second over meters squared. Okay, which gives us joules over meters squared times seconds. Okay, that's where that unit comes from. Okay, so let's think about waves and how sound waves and light waves travel in general, okay? As you get farther and farther from the source, what happens to the intensity of the wave?
It's less.
Yeah, it decreases, right? If you're farther and farther away from the source of the sound, it's quieter, right? So that's what we're thinking about here, but we're going to look at the ratio that goes with that, okay? Okay, so waves spread out three-dimensionally. And it's a uniform kind of spread, or, I don't know, I can't think of the word that I want to use. They travel in a uniform waves from that original source, okay? And what we're talking about here is that the intensity is proportional. Do we know that symbol right there? Okay, that means proportional to. You've never seen that? Like, kind of equal to, but not kind of equal to. Okay, it's proportional to. That's what it means. Okay, 1 over the inverse of the square radius. So this is the equation that I'm talking about that we're really going to use here. Your book goes into much more detail about where this equation comes from. I'm not going to do that. Okay, if you were really curious, you are more than welcome to read that in your book. I don't think it's all that important to see the derivation of the equation, but this is what we're talking about. So at any 2 points on the wave, we can see the relationship between the intensity of the wave at that point and the radius that it is from its source. Okay, so we can see it at the source and at a point far away, or at 2 points that are farther out from the source, either way.
So is that bottom one on our equation sheet?
I would put that bottom one on your equation sheet, yeah. Okay, so this would be the first point we're looking at. This would be the second point, both a distance away from the source. So we can expect that the intensity of the wave at those 2 points will both be less than the original intensity, right? This is hopefully common sense to us a little bit, but we're putting it into an equation form now. Okay. So we're going to solve this to look at the ratio. Okay, what is going to be the ratio of intensity of the first to intensity of the second? We don't have a whole lot of numbers here to plug in, except for that we're 3 times away from our original source. Okay, so let's look at our equation. Intensity of the first equals radius of the second squared over radius of the first squared over intensity of the second. Okay, we want to know the intensity that's 3 times away further. So what variable are we solving for? Which I? I1 or I2? I2. Good. Okay, so this is what we're solving for. What do we think R1 would probably be?
Just R.
It's just 1, right? If that's the original source, and we know this is 3 times further away, we're just going to make it a 1 and a 3. Right? We can make it a 2 or a 6 or a 3 or a 9, whatever we want. We just have to make the second radius 3 times larger than the first. Okay? So let's set it back up. We'd say I1 equals I2. 3 squared over 1. Right? Does that part make sense? Okay, so we're saying I1 is equal to 9 over I2. If I want to solve for I2, what should I do here? Switch those 2 places. So I would say I2 equals I1 over 9. Okay, so what fraction of the sound are we going to hear if we're 3 times away from the source? Yeah, we're going to hear 1/9 of what we would if we were at the source. Okay, it's because of that square value. That's it.